Okay, so I just really briefly wanted to go over how we can go about doing this experiment. So hopefully you tried it out, and now you can kind of check your work versus what I'm going to do. So this looks a little bit different, and I'm sorry about that. I just kind of took it from the AP website, and it's a little bit difficult to adapt it to the Google form. So what we're looking at here is we're saying students perform an experiment to collect data that can be used to determine the density rho L of an unknown liquid. They have a tall cylinder containing the liquid and some cubes of different sizes but the same known mass m that all sink in the liquid. They only have a meter stick and a stopwatch to take measurements. So we're going to say describe a procedure that students could use to collect the data needed to create a graph that can be used to determine the density of the fluid, including the measurements to be taken and any steps to reduce experimental uncertainty. So before I do that, before I think about collecting data, I want to think about what I need. Like, how am I actually going to get this rho L? So how am I going to figure out the density of this fluid? That's what I want. That's what I want to know. I know that I have mass of cubes. So I know that I have that. And I know that they sink. I have a way to measure distance. So I have a meter stick, so I can figure out distance. So meter stick. And then I have a stopwatch, so I can measure time. So those are really what I can work with here. So I want to think about what happens in this case. So when I drop a cube in here. So when I drop a cube in there, I know that it's going to sink. So I know that I have some sort of gravitational force on it. I also know that because it's in a fluid, there's a buoyant force acting on it. So I also have this buoyant force. So this is actually a kind of good place to be in because I know it's going to sink and I know it's going to fall at some rate. So I can go back to thinking about Newton's second law where I say, oh, the net force is equal to the mass times the acceleration of an object. So I can say, well, in this case, my net force is some positive buoyant force minus some force of gravity, Fg. And that equals the mass of my cube times the cube's acceleration. So then I can look at my equation sheet and start plugging some things in. So I know that I have an equation for the buoyant force that is rho, the density of our liquid, times g times the velocity that's displaced. Or in this case, it's because it's submerged, it's going to be the velocity of our cube. So then I'm going to say, well, Fg, that's just the weight force of the cube, so that's just equal to m times g. Writing it as this capital M because we're saying, hey, we know the mass m. And that equals m times a. So if I'm looking at this case, if I'm looking at my experiment, what I'm going to do really quick, just kind of highlight some things. So really the thing that I want is this rho L. That is what I want. And then I want to think next, well, what am I allowed to use? So I'm allowed to use this G, because I know that G is just 9.8. So that's okay. I have this. I have the capability to know it, the capability to use it in my equation. This M, they're telling me, oh, we know M. You know the mass of it. No worries about measuring it. You know it. So if I'm thinking about this, I have, I'm kind of setting up this weird key. But so yellow is what I want. So this is my wants. The blue is my haves, my givens. And then the final stuff is what I need. Maybe I'll put in this nice pretty pink color. This is what I need. So it looks like if I want to set something up, I'm pretty close. I just have a few things that I need. So I need volume of my cubes and I need A. So I can think about, well, what can I measure already? Like how can I get volume using my tools? And I know that I have a meter stick and these things are cubes. So really if I wanted to, I could just figure out the volume of my cube by measuring the base and the height and the depth. So this V is actually, this volume, that's actually something that I can measure with a meter stick. So I can measure this with a meter stick, and it goes from something that I need to something that I can measure. So maybe I'll call it need/measure. Then this last one, acceleration, this is a little bit tricky. So I'm thinking about it, I'm dropping this cube in the liquid, it's going downwards some sort of distance, maybe we'll call this some distance y maybe. Right, it's kind of following this depth y. So if I'm thinking about that, well, let's see. Well, I'm able to measure distance, I'm able to measure this y, I'm also able to measure time. I want acceleration, I want a, so if I'm thinking about this, I have like y, I have a, I have time, or I want this, but yeah. And then I also think about it, I'm kind of just placing it in there, so I know that my initial velocity is just, I can make that 0 if I wanted to. So if I'm thinking about this, well, it looks like I have something for distance, something for acceleration, something for time. If I think back to my previous physics, or I look at the equation sheet, which is equally valid, my equation sheet has these kinematics equations, where we can look at these kinematics equations and use them. So this one right here, if we're looking at it, has something about the distance that we travel, this x equals x naught. So these are all about distance. This v naught is my initial velocity. And then 1/2 at squared, that's related to my acceleration and my time. So let's come over here and write this equation. So we can say x equals x naught plus v naught t plus 1/2 at squared. So I can say, well, the x minus x naught, really the distance we're moving, that's just what I'm calling y. I said v naught, I can set this experiment up so that's just equal to 0 plus 1/2 at squared. I can kind of rearrange this and say 2y divided by t squared is equal to a. And if we're kind of thinking about this, I said I'm able to measure a distance and I'm able to measure a time using my stopwatch. This can be used by my meter stick, and that's my stopwatch. So I'm actually able to calculate a. I'm able to take enough data points where I can find a experimentally and then calculate it. So let's come back up to our experiment and say, well, rho L G times the volume, so volume G equals m, and then instead of a, we can put in our new 2y over t squared is equal to our acceleration. So this is actually pretty dang good. I have an experiment, and really quickly, I'm going to replace v. We're given that these are cubes, so let's just say that they all have this side length x, so instead of volume, we'll call it x cubed, just so it's in terms of our measured variables. Rho Lg times x cubed minus mg equals m 2y over t squared. And we said that we wanted the ability to figure this out with a linear graph. So if I'm looking at this, I want rho to show up in my linearized graph. I really want it to kind of act as like a slope. So if I'm thinking about what I have over here and what I'm measuring, really what I'm able to measure or control or change in this experiment, now if I'm kind of thinking about things that I can change, things that I can move around, I can really change, I'm able to change the height that I'm dropping it from, and I'm able to measure and change the time. So I really want to set something up that's saying as we change time or as we change y, probably y is going to be easier, as we change y, how does t change? So I kind of want to move some things around. So maybe I will multiply everything on this side by t squared and say rho L g x cubed minus mg equals m 2y. This is all multiplied by t squared. And yeah, then I got something going. And yeah, so we're kind of at a good enough point where we know what we want to do. We'll come back and we'll look at the linearized version of this. But so we're kind of at a point where we're saying what we want to measure is y, so the height that we're dropping from, and then t, time, fall. And maybe what I'll do, this is getting kind of long, maybe I'll leave that here and then I'll let you roll through with the rest. So thinking about linearizing and going from there. But so really what we're thinking about is, yeah, I guess this can kind of act more as a, if you're stuck, if you're very confused, you can watch this just because we're getting kind of long, so we can pick up with it tomorrow. But so if you're stuck, maybe think about this process in designing the rest of your experiment. So then I'll make another key and we'll start off tomorrow with that. So yeah, so that'll be kind of where I'm wrapping this up for today, just because things are getting a little bit long, but hopefully that's a good starting point for you to jump in at.